Have you ever stopped to think about that? Why can you twist a copper wire into any shape you want, but if you try to do that with a piece of coal, it just shatters? The answer to that question, well, it all comes down to one of the most basic ideas in all of chemistry.
Hey everyone, welcome. If you're gearing up for your Class 10 boards, you're in exactly the right place. We're going to do a super focused revision of a really important chapter, metals and nonmetals. So let's get right into it. So here's our game plan. We'll kick things off with the big split between elements, then we'll get into what makes them different, followed by a power ranking to see who's strongest. After that, we'll look at how we get them out of the ground, and finally, how we keep them from falling apart. It's the whole journey, from pure science to the real world. All right, first up, the Great Divide. Think of it like this. In the huge universe of all the elements, the very first way we sort them is by putting them into two giant buckets. Metals and nonmetals. And trust me, getting this simple difference down is the key to unlocking pretty much everything else. Okay, so how do we actually tell one from the other? Well, it's all about their properties. And we're going to start with the physical stuff. The things you can literally see, touch, and even hear. So what are the classic signs of a metal? First off, they're shiny, right? That's called luster. They're also malleable. That's just a fancy word for being able to beat them into thin sheets, like gold foil. Then there's ductility, the reason we can pull copper into super thin wires. On top of that, they're usually hard, they're sonorous, that's the ding sound a bell makes, and they're amazing conductors of both heat and electricity. Now, when you put them side by side, the difference is just obvious. Metals are shiny. Nonmetals are mostly dull. Metals bend. Nonmetals are brittle. They just snap. But, and this is a big but for your exams, you gotta know the exceptions. Iodine is a nonmetal, but it's shiny. And diamond, which is just carbon, is the hardest thing out there. So definitely make a note of those. You see, all those exceptions are exactly why physical properties can be a little unreliable. They don't give us the full picture. If you really want to know the difference, you have to look at how they behave in chemical reactions. And that brings us to their chemical properties. And what's the driving force behind all of chemistry? It's all about the electrons. Here's the deal. Every single element has one big goal in life, to be stable. And stability means having a full outer shell of electrons, just like the noble gases. You can think of it as their happy place. Now, metals and nonmetals, they just have totally different game plans for getting there. Let's look at the most famous example ever, table salt, NaCl. You've got sodium, a metal, with one extra electron it just wants to get rid of. And then you have chlorine, a nonmetal that's just one electron short of being stable. It's a perfect match. So, sodium literally gives its electron to chlorine. Now sodium is a positive ion, chlorine is a negative ion. And what do opposites do? They attract. And bam, they stick together, forming a super strong ionic bond. Okay, so we know metals are givers. They give away electrons. The obvious next question is, which ones are the most generous? Which metals give them away the easiest? That's where the reactivity series comes in. It's basically a power ranking for metals. Okay, everybody, pay close attention here. This slide is pure gold for your exams. You really need to learn this list. It's the reactivity series, and it ranks metals from the most reactive at the top to the least reactive at the bottom. Up top, you've got guys like potassium that'll literally react violently in water. And as you go down the list, they get more and more chill until you hit gold at the very bottom, which is so unreactive it can just hang out for thousands of years. This list is your secret weapon for predicting reactions. And here's how you use that list. It's all about something called a displacement reaction. It's like a king of the hill game. Any metal that's higher on the list can knock a metal that's lower on the list right out of its compound. So in this case, iron is higher up than copper. So it just waltzes in and kicks copper out of the copper sulfate solution. Simple as that. The more reactive metal always wins. So all this theory is fantastic. But what's the point? How do we actually use it in the real world? Well, let's talk about that. This is where metallurgy comes in, which is the whole science and art of getting pure, usable metals from the rocks we pull out of the ground. It's basically a 3-step process. Step 1, you concentrate the ore. That just means you clean it up, get rid of all the useless rock and sand and dirt. That junk has a name, by the way. It's called dang. Step 2, you extract the metal using chemistry, getting a sort of rough, crude version of it. And finally, step 3, you refine it, polishing it up to get that pure, shiny metal we want. Now, in that second step, extraction, there are 2 super important heating methods you gotta know. roasting and calcination. They sound similar, but there's one huge difference: the amount of air. Roasting for sulfide ores, you do in plenty of air. Calcination for carbonate ores, you do in limited air or even no air at all. But the goal for both? To turn the ore into a metal oxide, because that's way easier to reduce to the pure metal. But wait, what about those super reactive metals at the top of the list, like sodium or aluminum? They cling to oxygen so tightly that just heating them won't work. For those guys, you have to bring out the heavy machinery, electrolytic reduction. This basically means zapping them with a huge amount of electricity to force them apart. Okay, so we've done it. We've got our pure metal. Awesome. But we're not done yet. The journey isn't over. Now comes the hard part: keeping that metal safe from the elements and sometimes making it even better. And what's the number one enemy of most metals? Corrosion. You see, metals kind of want to go back to how they were in the ground, in their more stable ore form. Corrosion is just that process happening. Rusting on iron is the classic example everyone knows, but it's also the black stuff that appears on silver or that green coating you see on old copper statues. The good news is we have a whole arsenal of weapons to fight corrosion. The easy ones are just putting a barrier up, like paint or oil or grease. But then you have cleverer tricks like galvanization. This is so cool. You coat iron with zinc, which is more reactive. So when nature attacks, the zinc jumps in front and corrodes instead, sacrificing itself to save the iron. It's like a metallic bodyguard. But maybe the smartest method of all is alloying. This is where we get to be creative. We start mixing different metals together, or even a metal with a non-metal, to cook up a brand new material that's way better than the original. And you see this stuff everywhere. Think about it. Pure iron is actually pretty soft and it rusts like crazy. But mix in some nickel and chromium, you get stainless steel. Tough, shiny, and it doesn't rust. Or mix copper with zinc, you get brass. This is literally how we design materials for specific jobs, from the spoon you eat with to the tiny parts inside your phone. All right, let's wrap this up with something to think about. With all our high-tech labs and scientific knowledge, you'd think we know it all, right? But sometimes the past has secrets that can still blow our minds. Just think about this number, 1600. Over 1600 years. That's how long the famous Iron Pillar of Delhi has been standing out in the open through rain and sun, and it is barely rusted at all. It's an absolute masterpiece of ancient metallurgy. So here's a final thought for you as you study for your exams. What did they know back then? What secret recipe, what incredible level of skill allowed them to make a piece of iron that just refuses to rust? It just goes to show you, the chemistry we're learning about today isn't just for exams. It's been at the heart of human innovation for thousands of years.